Alright, so yesterday we introduced few tools like variational, semi-norm, oscillation semi-norm, and lambda drums. We discussed them, and also at some point we proved that lambda drums with parameter 2 are endpoint for R variations with R greater than 2 in particular. And today the plan is to introduce the structure, well, more general than just the classical dynamic structure, and also give a proof of lagging time estimate. That is, I would like to give you a proof. First, I would like to give you a proof of lambda drums with parameter 2 for quite general martingale, but not very general. So this will be a martingale, which is similar to the classical dynamic structure. Okay, so first let us recall the classical dynamic structure. So we have unit cube, which is 0, 1 to the power d, and I decided to make the right endpoint open, but it does not matter. So then, considering congruent cubes, we have dyadic cubes from generation 0, so these are cubes of this type. So we add integers to unit cube. Then we can dilate those cubes by dyadic numbers. So we obtain kth generation of dyadic cubes, and if we sum all of those generations, then we get just dyadic cubes. Okay, so dyadic cubes consist of dyadic cubes of generation k, and we make this definition such that if the generation grows, then the length of the cube decreases. And this is because when we later on consider averages, we want to have that if k tends to infinity, then the averages converge to the function itself. Okay. So what are the properties of dyadic cubes? The first one is that if we consider the sum of all dyadic cubes from generation k, then we obtain RE. So in other words, any point belongs to exactly one cube from generation k. Another very important property is this one, is that if we have two dyadic cubes, then essentially there are two possibilities. The first one is that those cubes are disjoint, and the second one is that one of them is contained in the other. And the last property is that okay, so the other property is that if we consider a cube from generation k, then in the previous generation we have a father of this cube, in the sense that this cube is contained in some cube q0 from previous generation. Right. And in a moment, I would like to tell you that in fact this structure can be obtained in a much more general situation. So in order to introduce this, first I need to introduce this more general situation. So first there is a definition of quasi-metric. So the definition is exactly the same as the definition of the metric, except the triangle inequality. So instead of having triangle inequality, we allow a quasi-triangle inequality, in the sense that we allow this constant a0, which is at least equal to 1. So if a0 is 1, then we have a metric, and if a0 is greater than 1, then we have a truly quasi-metric situation. And this causes some problems. So in fact, in such a general situation, we can introduce balls in exactly the same way as in the case of metric. So these are points to the ball centered at x and with radius r, consists of points in x, such that this quasi-triangular distance is smaller than r. But the problem is that if 0 is strictly larger than 1, it may happen that those balls are not open. So we define open sets such that if the point x belongs to open set, then it means that we can find a ball and with some radius and centered at this point x, such that this ball is contained in U. But it may happen that balls itself are not open. Okay, so this is a bit problematic thing, but on the other hand, there is a result of Macias and Segovia, who proved that in such a general context, it's possible to introduce another quasi-metric rho prime, which is comparable, and in this new quasi-metric, all balls are open. Okay, so from our point of view, in fact, at the very beginning, we may think that all balls are open. Because for us, it wouldn't matter if we consider rho or rho prime, which is comparable with rho. Right. So then, having quasi-metric, we would like to add measure. So we consider measures on quasi-metric spaces which satisfy a doubling condition, which means that we have this estimate. So it means that if we take any ball and be with center at x and with radius r, and if we consider ball which is concentric but with twice larger radius, then the measures of those balls are comparable uniformly with respect to x and r. In fact, it does not matter if we take the constant 2 here, we may take any other constant. It's equivalent. So if we have it for 2, then we have, in fact, this estimate for any other fixed number. What changes is this universal constant A1. All right, and I would like to consider spaces of homogeneous type, and these spaces are quadruples, such that the first triple is a quasi-metric space, and we add measure, which is doubling. Further, we assume that the balls are open, and also we assume that the measure of each ball is finite. In fact, what we also want to have is that the measure mu is non-zero on some ball, and this implies that it is non-zero on balls. Just using this doubling condition, it can be easily deduced. If we have one ball with a non-zero measure, then all balls measure. All right, and here are some examples of spaces of homogeneous type. So the first one is R with Euclidean distance or any other distance, which is comparable to Euclidean and with power of weight. So x to the power alpha with alpha greater than -1. So we want to have integrability around 0. So this is so in particular with Lebesgue measure we have a space of homogeneous type. On the other hand, sorry, it should be alpha smaller or equal to -1. Then we do not have homogeneity because in particular balls around 0 have infinite measure. And similar situation is if we consider interval 0, 1 and power weight of these types. X to the power alpha, 1 minus x to the power beta, alpha beta greater than this one. And then still we have a space of homogeneous type. Another example which from the point of view of my talk is quite important, but we will not see this explicitly, is the following quasi-metric. So this gives in fact the structure such that on the first coordinate we have just scaling of type 2 to the power k. Then on the, well, or t, on the second coordinate, we have t squared. On the third one, t to the power 3, and so on. And on the last one, t to the power d. Okay, and this quasi-metric, in fact, is useful when we consider Bourgain's polynomial ergodic theorem for general polynomials. So if we consider polynomial of degree d, then we need to use exactly this quasi-metric in the later on. Okay, so this is quite useful, and in particular in that situation we do not have metrics. So it is indeed quite convenient to consider such general set. All right, and here we have an example of a space which is non-homogeneous. So the problem is that even if we take alpha equal to 0, the problem is that this exponential function has a very rapid decay at infinity. In fact, what is quite useful, and implicitly we will use this during my talk, is that there is some sort of dichotomy in the sense that the space is of homogeneous. Well, if we have a space of homogeneous type, then the measure of the whole space is finite, if and only if the diameter of this space is finite. Okay, so this in particular, if we know that, this in particular, having this knowledge, we can easily construct an example such that we have a space of homogeneous type and we take a subset of this space, and this subset is not a space of homogeneous type, which is a bit annoying in this theory. That subsets of spaces of homogeneous type are not necessarily spaces of homogeneous type. But what is also important is that if we restrict our attention to, okay, I will tell that later on. The point is that we will be able to construct the ergodic structure, and if we restrict our attention to the dyadic cube, then we still have space of homogeneous type. All right, so in such a general situation, we can introduce Hardy-Little maximal operator because we know what is involved. So we construct Hardy-Little maximal operator for locally integrable functions. By locally, I mean that the integrals over all poles are finite. And in such a general setting, using Vitali type argument, it's possible to prove a weak type one expansion. Since L infinity bound is trivial, we have the boundless for t between 1 and infinity. It is also possible to prove that we have a very nice dense class that is continuous functions with bounded support. So using these two facts and this two-step procedure, which I mentioned during the first talk, we can easily deduce that we have Lebesgue differentiation theorem. That is, if we consider limit of such averages when R tends to 0, then we just get function f for almost all x's, and it works. Since this is local, since this property is local, in fact, it works for all L1 locally integrable functions. All right, do you have any questions? At some point, we will restrict our attention, in fact, to the classical situation of RD with the n cubes, but for a moment, I would like to introduce this very nice theorem by Michael Christ from 90s. So this is the theorem. So it tells us more or less that if we have a space of homogeneous type, then we may think that we have analogous structure as in the case of RD. That is, we have dyadic cubes. Please do not take an attention to those constants. I will try to explain them when we will look precisely on each property which we have. So in fact, we have two universal constants. One comes from the quasi-metric. So this is a constant coming from the quasi-triangle inequality. So this is A0. And we have second universal constant, which is A1, and it comes from doubling condition. And having only these two constants, we can find this all other constants. So they are also universal once we know constants A0 and A1. And the first property of this structure is that, okay, so we have dyadic cubes. So we have dyadic cubes of generation K. And what happens is that if we consider all cubes from generation K, then they almost cover all space X up to measure 0. And we cannot avoid that because we assume that the dyadic cubes are open. So in particular in RD, when we consider dyadic cubes, they were half open, half closed, right? So here we should expect that the composition is up to some error. And one remark is that it's quite inconvenient to think that we may just throw away this set of measure 0 because somehow we can throw away the centers of the balls, which are somehow related to those cubes. So we should think rather that this decomposition is up to full measure, but not just that we throw away those bonds. Already, the second property is that, well, this is the property that we have just two possibilities, that the cubes are disjoint or one is contained in the other. And here we use exactly the same, well, here we have exactly the same order. That is, if we consider cubes from generations which are larger and larger, then the cubes are smaller and smaller. Okay. The third property is that if we have dyadic cubes from generation K and we consider generations which are smaller, that is, cubes are larger, then there exists exactly one cube from the generation which is smaller, such that our original cube is contained in this cube from generation L. Point number 4 tells us that each dyadic cube has finite and uniformly finite number of children. So this N0 is a universal constant, which depends only on this universal constant N0 and K1. Point number 5 is that more or less we may think that those cubes are balls. Okay, they are balls, and the radius is more or less kappa to the power k. So in the classical situation, you may think that kappa is 1/2. In general, it's a very small number, and we cannot control it in the sense that we may assume that it is as small as we wish, but in particular, we cannot claim that it is 1/2. Okay? But it does not make any problems in the analysis. And the last property, which we will not use, is that essentially it's not true that the mass of the cubes is concentrated on the boundary of the cube. Okay? So it may happen that we have a very large mass on the boundary, but it's not that we have all mass on the boundary. Okay? So these are 6 properties for these cubes, which makes this homogeneous spaces of homogeneous type look a bit similarly as RD. Okay, so the analysis will be very different. All right, and having such a general context, that is, if we consider spaces of homogeneous type, then we may think that we have fixed dyadic structure. Okay, from now on. What we can do is we can relate with this dyadic structure filtration. So filtration at the level K is sigma algebra generated by dyadic cubes from generation K. So what happens is that if the parameter K grows, then the filtration is larger because we have smaller dyadic cubes. In fact, if you do not like this very general context, from now on you may think that we have just RD and the classical band cubes. It's okay. Right, and so having this filtration, we can define the corresponding conditional expectation operators, EK. So these are just averages over dyadic cubes from generation K. So for a fixed X, well, for almost all X's, there is exactly one dyadic cube from generation K, and this operator is just averaging over corresponding cube. Then we can also consider martingale differences. So dk is a difference of ek minus e from generation one less, and what we can easily prove some properties of these two operators, which are not very hard to see. So the first one is that on each cube from generation K, this martingale difference is constant, and this is quite easy to observe because actually EK is constant because it is an average, and also EK minus 1 is a constant because it's in fact constant on the father of these cubes, in particular on this cube. Right, and on the other hand, if we consider a cube which is from generation K minus 1, then what happens is that the integral or the average of their difference is equal to 0 because in fact the integral over q of ek is just an integral of the original function f over q, and the same for that. So we have two integrals over q, so it's 0. Then using the fact that this is a conditional expectation, we have this identity. So in particular, it tells us that ek commutes, and if we compose ek with en, then we obtain e with index which is minimum of these two indices. As an operators on L2, they are self-adjoint, both ek and ek. In the case, it's a consequence for ek. And then we can also prove that dk are orthogonal even if we take different functions. So function f here, function g there. So one can prove it just using this first observation and writing it down. Okay, so assuming that, let's say k is smaller than k prime, and write down the corresponding integral and decompose it into cubes from generation k prime minus 1. So the larger parameter minus 1. Okay, and using this observation. And then let us skip this one and let us go to those three, because this one will be in fact the consequence of those at the bottom. So the first observation is that if we tend with k to negative infinity, then we obtain this average. This average is understood in the following way. So if the measure of the space is infinite, then this is just 0, whatever f is. And if it is finite, then this is just an average. And it makes sense for all LP functions, because if the function is in LP and the measure is finite, then it's in L1. All right, and this is quite useful. Even, well, considering finite spaces is useful, even if we restrict our attention to the classical situation of RD, because sometimes it's convenient to start dyadic decomposition at the level of the unit cube. So we start from the unit cube, so formally our space is fine. Okay. All right, another property is that if k tends to infinity, and then the averages tends to f almost everywhere, and this follows from the fact that, well, from the Lebesgue differentiation theorem. So here we need to know that the maximal operator is of type 1, 1. And the last thing is that the sum of decays is essentially equal to F, and it follows from these two properties and the fact that we have a difference. Right, and having this and knowing that decay are orthogonal, we can easily see that this inequality happens because we might have on the left hand side additional term if the measurement space is finite. If it is infinite, then actually we have identity. Right, any questions? Okay, so let us now consider maximal dyadic maximal function. So it is defined as a supremum over all averages, and we put absolute value of f here. So everything is positive, well, non-negative. And there is a theorem which tells us that this dyadic maximal function is of U type 1, and it is bounded on L infinity. And using Marcinkiewicz interpolation theorem and trivial L infinity bounds, it reduces to showing weak type 1. So this is that. Well, I need to prove this result because later on I will need Calderon-Zygmunt decomposition, which naturally comes from the proof of the weak type 1. So here we have two possibilities. First one is that t is smaller than this average. So then we get this estimate for free because the left hand side can be estimated by the measure of x, and this is smaller than L1 norm divided by t. This is easy, so we may assume that the opposite situation happens. And here what we do is we use stopping time argument. So somehow we know that at infinity we didn't cross the limit, the level t. So what we do is if we assume that x is in this set, it means that at least one average is greater than t. And at infinity, we have the opposite estimate, so it means that we can find the maximum dyadic cube, for which we have this property that the average is greater than t. Okay, so having these maximal cubes, we can easily see that this level set for the maximal operator is equal to the sum of those chosen dyadic cubes QJ. All right, and what happens is that we can estimate the measure of this set by the measure of the corresponding by the sum of the corresponding measures of the cubes QJ, and we use the fact that they were chosen in the way that the average is greater than t. So in fact, we have this estimate, and finally we use the fact that they are disjoint. So we can estimate this sum of those integrals by L1 norm. And this is the end of the proof. But what will be useful for us is in fact that we have the following decomposition, which is called the Calderon-Zygmunt decomposition. And so if we assume that t is greater than this average, so in particular if the measure of the whole space is infinite, we consider all positive t's. Then we can construct a family of pairwise disjoint dyadic cubes such that we have these three properties. So the second one is just the fact that the dyadic maximal function is of weak type 1. The third one comes from the fact that QJs were maximal such that the average was greater than t. We have this estimate. So if we consider a father of Qj, then we have the opposite estimate. And using that, we can easily see that in fact those averages are comparable with T. On the other hand, if X does not belong to the sum of Qj, this means that every time we consider at every generation, when we consider averages with the corresponding dyadic cubes, they were smaller than T. So if we use, so it means that the operator Ek at point X was always smaller than T. So using the fact that those operators tends to F when K tends to infinity, we know that f of X is smaller than T for almost all X's. All right. Do you have any questions? Let's see. All right, so now I would like to focus on the main theorem I would like to discuss today. That is Lepine type estimates. So we are in this general situation of spaces of homogeneous type, and we have this dyadic structure, and we consider this averaging operators. So I stated as a main theorem, I stated the theorem in fact, by Pizier and Tissot, because I would like to give a proof of this theorem. But historically, the first theorem of this type belongs to Lepine. So he was able to prove R variation estimate for these dyadic averages for all R greater than 2. Here, the theorem of Pizier and Tissot is analogous result for lambda jumps. So for lambda jumps with parameter 2, we know that we have lambda jump estimate for all p greater than 1, and we have the corresponding with type 1 estimate. And these results are sharp in the sense that it's not possible to prove two variations for these averages. And this is quite complicated counterexample, which was constructed by Jones and Wang in 2004. And it is based on some technical result by Qian from 98, which is kind of iterated, the law of iterated logarithm. And this is quite complicated example, but at the end, it's possible to find a function which is uniformly bounded and supported in the unit interval, such that two variations are infinite for almost all points. Yes.
For the bingle, you have a space X, and for the sharpness for B2, you have PR.
Yeah, okay, because what happens is that it's possible to find this counterexample for the classical dyadic structure. So it suffices that you consider R with the classical dyadic cubes, and you can find a counterexample. Because it's not a counterexample which is global, because I didn't think about that, but I can imagine that if you take a space which consists of one point, then probably you have variations. So the counterexample is not that it works for all the spaces of homogeneous type, but for the particular one, and you can find a counterexample for the classical dyadic space. All right. There is a similar result for two oscillations. So it was proved by Jones, Kaplan, Rosenblatt, and Pierre that two oscillations, that dyadic averages has bounded to two oscillations for all p greater than 1. and there is also analogous result for a weak type 1-1. And this result is also sharp. That is, if we consider row variations with row smaller than 2, then it's possible to find a counterexample to this estimate. In fact, it's possible to do something stronger. That is, in the definition of the row oscillations, we have some supremum. So we consider a supremum in some blocks. And here it suffices to consider a fixed sequence of I k. Right? So this is somehow something stronger because this for rho equal to 2, this is just a square function. Okay, so this is a row function, and even for this row function, we can find a counterexample in the sense that the right-hand side here would be infinite for almost all x's. Okay, and this counterexample, in fact, is much easier than the counterexample for row variations, but this is not surprising because for R variations, we are at the endpoint, R equal to 2, and here the endpoint is, for the endpoint, we have a positive result, and we consider rows which are smaller, so this is not an endpoint. We are close to the endpoint, so the intuition is that the counterexamples should be much easier. And this is indeed the situation here. In fact, the counterexample is based on Rademacher functions. This is like half a page of analysis. All right. So from now on, I would like to give you the proof of lambda jump estimate for this for the martingale. So first, I would like to prove LB estimate, and at the very end, I will give you a proof of weak type 1-1. In fact, once we will have L2 boundedness, the weak type 1-1 will be very simple. Okay, so the main thing here will be to obtain L2 boundedness, and then weak type will be very easy. Okay, so what happens here is that instead of considering original lambda jumps, well, maybe it's worth to let you know, well, to remind you what is the definition of lambda jumps. So the definition is that we have a fixed level lambda, and then we look at the consecutive jumps which are of height at least lambda. And this is this counting function and lambda. Okay, so we are looking at the consecutive sequences such that the martingale averages are greater than the lambda. And the first thing we can do is that instead of looking at the original counting function and lambda, we can terminate this lambda counting function to the interval minus n. So we are looking for sequences of points such that they are between negative n and n, capital N, such that in each interval we have a jump of height at least equal to lambda. And then if we were able to prove this estimate with this new truncated lambda jump counting function, then by limiting argument, we will be able to prove the original estimate once our constant does not depend on this capital N. So the first thing we want to do is to construct a stopping times tau j such that our left-hand side here will be dominated by the square function based on those stopping times. So, and by stopping time, I mean that, well, this is the classical definition that if we consider each tau j, then the set that tau j is smaller than n is Fn measurable. Okay, and this measurability will be crucial in our argument. So it is, well, it is very, we need to be quite careful to be sure that this is Fn measurable. All right, so what happens here is that we start with tau 0 a bit artificially. We put that this function is a constant function, which is equal to minus n minus 1. And in fact, we are interested only in the interval minus n. So we put something which is much smaller. And then what we do is we look at the first time. So tau jx, it will be the first time when we have a jump of height lambda half of the lambda after the previous one. Okay, so we think that tau j minus 1 is already chosen, and we take the minimal parameter k such that we have a jump of height lambda by 2. Okay, and we use this convention that with this set, so if we already find all jumps of height lambda over 2, then we put that this tau is equal to n plus 1. So if the set is empty, then we put n plus 1. So this is also a bit artificial, but what we want to have is that this these stopping times tau j, they increase, and they in fact increase strictly unless we have a situation that we do not have any jumps. Right? Because if we still have some jumps, then k is chosen in the way that it is strictly larger than the previous. Okay? All right, so we have two situations. The first one is trivial, so there are no jumps. So the left-hand side is equal to 0, so we trivially have our A. And in the opposite situation, we assume that we are able to, we have j jumps, so we can find a sequence tj such that we know that we jump by a number which is larger than lambda. And here we start to play this game, that if we have two numbers such that the difference is greater than lambda, well, the absolute value of the difference is greater than lambda, then it does not matter how we choose another point, the distance between this new point from one of the endpoints is at least equal to lambda over 2, right? Because this follows from the triangle inequality. So in that way, if we know that there is a jump between tj and tj plus 1, then if we start from the point which is tau j minus 1, then the distance between this average and one of those endpoints is at least equal to lambda over 2. So it means that our jump is obtained at most at the largest points from this. So in that way, we can omit some jumps, but we can detect at least half of them, more or less half of them. Okay, so what happens is that we are able to detect at least half of the jumps, and instead of detecting original jumps, we detect the jumps which are half smaller. So that's why we have this form. This is a combination that we omit. We might omit half of the jumps, and also we look at the jumps which are half small. Right, and it is crucial to observe that if we choose stopping times in the following way, that we take the minimal element of this set, this choice is such that tau j is indeed stopping time, and that is this set is fn measurable. And this follows from the fact that ek is fa measurable, and one can easily check. All right, so now we will need Hinton inequality. So we need to define Rademacher functions. These are so the first Rademacher function is such that it is okay. These are functions on the interval 0, 1. The first one is such that it is equal to 1 on the interval 0, 1/2, and -1 on the interval 1/2 1, and then we split everything diagonally. So the second Rademacher function is 1 on 0 1/4, then on 1/4 1/2 it's -1, then on another interval of length 1/4 is 1, and then -1, and so on. And one can easily see that this is an orthogonal system, but it is not complete. And we have the following estimate, which is due to hinges, which means that if we take a sequence which is in small L2, then if we consider a function on an interval 0, 1, such that each Rademacher function has a coefficient an, then it happens that all LP norms are more or less the same. So they are equivalent, and they are, so any LP norm is comparable with L2 norm, and L2 norm by orthogonality is just small L2 norm of the sequence A. And we will use this inequality because it is quite useful, because instead of considering a square function, we may consider this kind of sums. So in some sense, instead of considering square functions, we may consider some sort of singular integrals. So in particular, these operators will be linear, and it will be much easier to deal with them. So far we have shown that our original lambda jump object is dominated by some sort of square function. This is not truly square function, because instead of having parameters which are fixed, we have functions in the parameters. But what we can do is we can apply Hinching inequality, and instead of considering this square function, we can consider those sums. So here, epsilons are just signs. So we have plus or -1, and we want to get LP bounds for these sums. So you may think that these are the prototypes of singular integrals. All right, so the first observation is that we can use martingale difference, dn, and write down this difference in terms of dn. So that's why this second sum appears. And then we can switch the order of those two summations, and we can get this object when this epsilon tilde is exactly this expression. But now the observation is that if we fix m, what happens is that only one term here is non-zero. And this is exactly the term which corresponds to this side. Okay? Because what happens is that we take the maximum j such that tau j is strictly smaller than n. This is the only term. All right, but what is here important is that this inequality is strict, which means that this object here, this function here as a function of x, is f(n-1) measurable. Okay, so instead of considering these sums, we can consider operators tj, t sigma, which are of this shape. So instead of considering this epsilon and tilde, we can just put any sigma n and assume just that those functions are fn-1 measurable. And we want to, now our task is reduced to prove LP estimates for these linear operators. So what happens is that if we look at p equal to 1, then our task should be relatively easy, because so far we know that these martingale differences are orthogonal, and we can strongly use the fact that these functions are fn-1 measurable, and in that way we are able to show that in fact if we consider two terms with different indices, then the integral is 0. Okay, I'm sorry, but I do not want to go into the details because I have just 10 minutes. But well, one can easily prove that they are orthogonal. And once we know that, then the L2 norm squared of our operator is just the sum of the squares of the consecutive terms, and we use the fact that sigma n is smaller than 1, so we have this estimate, and at the end we use the fact that essentially f is equal to the sum of the ends, so the sum of the squares is dominated by the square of the L2 norm of and in that way we obtain L2 boundedness of the operators P sigma, and the reason why instead of considering this particular situation, we choose to consider more general case of such operators is that essentially these operators are self-adjoint in the sense that if we compute the adjoint operator to T sigma, this is essentially T sigma up to putting conjugate. So this is in the same class of operators. So that's why if we consider LP boundedness, it suffices that knowing that this is L2 bounded, it suffices to prove with type 1. All right, and here is the place where I need Calderon-Zygmunt decomposition. So we have two cases when we want to prove weak type 1. The first one is trivial, and the second one is that T is greater than the average over whole space. So if we have T and the absolute value of F, then we can construct a Calderon-Zygmunt decomposition. So we have dyadic cubes which satisfies these three properties. So these are exactly the same properties as we had before. And then we can define two functions. Good function, which is good one. So if we are on the chosen dyadic cube, then this is just an average of F. And if we are outside all cubes Qj, then we put F of X. On the other hand, when defining functions Bj, if we are on a cube, then we define the function Bj as here. So this is F minus the average. So in particular, an average of over Qj of the function Bj is equal to 0. And if we are outside cube Qj, then we put 0. All right, so this is what we have done. And now we can easily observe that F can be written as G plus B, where B is a sum of all bad functions. Well, one can easily see that L1 norm of G is dominated by L1 norm of F, because here we have averages, so this can be easily seen. Then the L infinity norm of G is smaller than T, because we have this property and also the first property there. This is what I've already mentioned, that the integrals over Qj of all j's are 0. This follows from also from the fact that the averages over absolute value of F is comparable to T, and this follows from the fact that the dyadic maximal operator is of weak type 1. This is done. Okay, and having this information, we can easily conclude the proof. Well, once we have one additional thing, that is when we know that the averages over well, it's the martingale averages on functions Bj are supported in the corresponding cubes Qj. And this can be easily seen because in the definition of these averages, only two situations can happen. So we can have the situation that the corresponding cube is disjoint with Qj, and then we get 0, or the other one is that Qj is a subset of Q. We cannot have the situation that Q is a subset of Qj. This is crucial to have that. And this means that if we look globally at the operator T sigma on the function B, which is sum of all J's, then the support of this operator is in the sum of all cubes Qj. So this means that if we look at the complement of this set, then what happens, since f is equal to g plus b, then the operator T sigma on f is just the same operator on g. Okay, so if we look at the weak type 1, then what happens is first we consider the set, the subset, which is the sum of all cubes Qj. So this part can be dominated by the sum of the measures of Qj. And the second part is the complement of this set. And on the complement of this set, T sigma f is just T sigma g. Okay, this is what we had before. Okay, so this proof is quite similar as in the classical Calderon-Zygmunt theory, except that here the situation is in fact much easier, because we have this nice property that the support of the bed function is contained in the sum of the chosen dyadic cubes. All right, so the first one, for the first one, we use just this estimate here, so we get what we want. And for the second one, we use the fact that the operators T sigma are L2 bounded. So what we get is this expression, and we use the fact that the L1 norm of G is smaller than L1 norm of F, and also that L infinity norm of G is smaller than T. So this will give us this estimate. These arguments conclude the fact that lambda jumps are LP bounded. And now there is a proof of weak type 1, which is very simple once we know that we have L2 boundedness. Because we simply use a similar trick as on the previous slide, that is, we use the fact that the support of P KB is in the sum of our chosen balls. So then, if we consider this level set, we can split this set into two pieces as before. So the first one corresponds to the sum of the cubes Qj, and the second one is the complement of this set. Right? And we can use the same trick as before, so we can replace EKF by EKJ on the complement of those cubes, and then we have just what we want for the first part, and for the second part, proceeding exactly as before, we use Markov estimate, and we dominate this by the corresponding L2 norm. So now we know that this operator here is bounded on L2. So for the second term, we get this expression, and once again, using this simple observation that G has smaller L1 norm and L infinity norm is smaller than T, we get what we want. Okay, so here in fact, weak type 1 is very easy once we are able to prove L2 boundedness. All right. Okay, so I will finish in 2 minutes. So what we have is that once we know that we have lambda jump estimate for martingales, And from what we've learned yesterday, that we can obtain R variations for R greater than 2 if we have lambda jumps. We can easily conclude that we have R variations for martingales, but then we want to upgrade this situation. So instead of considering martingales, we want to consider bound functions. All right, so we want to have a corresponding estimate for a bound function. By bound function, I understand that we have a smooth function. Let's say it's a function from a Schwartz class, which is symmetric, real, with integral 1, and we consider L1 dilations. So L1 norm of those functions psi t is equal to L1 norm of psi, so this is equal to 1. And then it's possible to prove that the R variations, well, here along the dyadic scales, are bounded on LP. And this is thanks to Jones, Zeger, Wright, because they were able to prove this well, technical estimate, which is crucial in the proof that we can transfer R variational estimates from martingales to these bump functions. And here, in fact, these assumptions that we have integral 1 and well, the function is real and symmetric are not very important, because once we have R variational estimate for one bump function, then using some sort of Littlewood-Pelmy arguments, it's possible to prove R variations for any other smooth bump function. Okay. All right, I'm not planning to, well, I do not have time, so I am not planning to give you the proof of R variation estimates for bump function, but later on I will just use that we have boundedness for bump function. And tomorrow I would like to finally give you well, the sketch of the proof of the Bourgain's ergodic theorem for squares. That is, I would like to give you a proof of L2 boundedness of R variations for squares. Okay. So thank you very much for today.
Thank you very much, Tomek. Are there any questions?
I just have a comment to that lemma there. It's the key that what makes that work is that fact that might prove that there's not too much mass that accumulates near the dyadic, the boundary of the dyadic cubes.
Yes.
That last property you put.
Yeah.
That was essential to get this decay estimate of 2 to the minus sigma k.
Yeah, that's right. That's right. Well, it's quite interesting, because if you just want to perform the Calderon-Zygmunt theorem, then you do not need to use this property. But if you want to, here it's important. Also, I think that it is important in Mike's paper when proving some TB theorems. He also uses this property. Yeah.
Actually, it works for a being between 1 and infinity. So you have interpolation with 3 and
This lemma.
yeah.
Yeah, the same as
But probably works for a being.
okay, it might be for LP.
Strict between 1 and infinity, right?
Okay, let me think.
On the right, you have DM, so you don't use that. If there was no DM on the right, then of course, right?
Yeah.
If there is a DM, if it was invertible, then also.
Let me think.
Yeah, I'm not sure.
Yeah, I think it's only for L2. Okay, we may.
It was on the end.
Yeah, okay, it's for L2. Yeah, it's for L2. I think it's for L2, because we just need this for L2 boundedness. For weak types, somehow we use Calderon-Zygmunt decomposition. So in order to get LP, I think you need just to have this for L2. That would be my guess. But well, we can try that.
Okay, so again, thank you very much, Tomasz, for a very nice talk, and we continue tomorrow with the lectures, and today we meet at 7. Okay. And now we.